All right, welcome back. We have another tool to learn about. Remember, a lot of statistics is just learning different tools for different situations. In the previous video, we saw one tool which can allow us to do problems like this. So we could figure out, hey, is there a variance of 4 minutes or less in arrival time? And so that's hypothesis testing about a population variance, a single population variance. In this video, we're going to see hypothesis testing about two population variances, right? So not just a single population variance, but two populations variances, and doing a hypothesis test about the variances of those two populations. And so that'll allow us to do things like if we had two different production facilities, two different production processes, right? We could look at or not only facilities, but we could have two different processes at the same facility. We could look at the product quality that results from those two different facilities or those two different processes. And so maybe one process gives us better quality with more consistency, less variance than another process. That would be good to know. And we could look at temperatures for two different heating devices. So let's say we manufactured two different kinds of heating devices, and we could look at the variance in temperature about those two different devices. And we could make a determination, this one's better, it has less variance in temperature. Or maybe there's two assembly methods. And we could look at how much variance in there is in assembly time from one method to another. So this really allows us to start making decisions about what is more effective and what's more consistent, which varies less. And so to do this, we're going to use data collected from two independent random samples. And so there'll be two populations. So we'll get data from from population one. We'll also get data from population two. And the two sample variances will be the basis for making inferences about the two population variances. So remember, we're going to get samples, right? Random samples. And those samples will have variances. And based upon those variances, we'll make inferences about the population variances. So to do this, we have a new test statistic. We have the F statistic. And so we've been learning about different types of test statistics. And we've seen the Z table, we've seen the T table, we've seen chi-squared. I think we've seen the T table, haven't we? Maybe I just read ahead. And then we also have this one right here, which is the F test statistic, the F distribution table. And so if you look at those, here's what the Z one looked like. And the rest of them kind of look like this. And so it's just sort of all iterations on that. But you'll notice here we have denominator degrees of freedom and we have numerator degrees of freedom. And then we also have area in upper tail, which is the 0.1, 0.05, 0.025, 0.01. So how much area in this upper tail here. So we're going to use this new test statistic, and it's F. And so we use what I think of as the F table to do that. And here's the F distribution. Entries in the table give F alpha values, where alpha is the area of probability in the upper tail of the F distribution. For example, with a numerator of 4 degrees of freedom and 8 denominator degrees of freedom and a 0.05 area in the upper tail, F 0.05 is equal to 3.84 would be your test statistic. And so if you looked up 4 degrees of freedom in the numerator, here's the numerator, 4 degrees of freedom, and 8 degrees of freedom in the denominator. That's going to be on the next page, so I could bring that up. And here's the next page, and let me just bring it over. Dun, 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 dun. Here it is. And so here's 8, and here we had 4. And at 0.05 with 8 and 4 is like 3.84 right there, 3.84. And if we go back here and we look at wherever, that example is right there. Right? And it's 3.84, right? So 3.84. So that's how you use that one. So we're going to see that in action. So you could do a one-tailed hypothesis test, right? Like that. And here are their criteria for rejecting or not rejecting. Or you could do a two-tailed, test like this one are the variances, the sample variances in the two populations. We will be using those to estimate and determine whether the hypothesis about the population variances in the two populations are equal or not equal. And again, making our decision, we have this information right here. So I'll just put that here, right? And what we're looking for is the null is nothing's changed, current state, no change, status quo. And null is also where equality resides. So that would be that right there. So here's an example of how you do hypothesis testing on the variances from two different populations. And so again, this first sentence is an example of how people who do statistics don't really know how to use English very well. And I feel like I've been doing statistics and I'm not even saying that very well. But basically they want to see which bus company they should choose for service, Millbank or Gulf Park. And they say Dulles County School wants to select one among the Millbank Company and Gulf Park Company for the bus service contract for the coming year. That's a horrible sentence. If I was doing this, I'd take this and drop this and put this into ChatGPT and say, can you please rewrite this sentence to make it better? And we'll see what it comes up with. Dulles County Schools deciding between Millbank Company and Gulf Park Company to award the bus service contract for the upcoming year. That's pretty good. All right, the variance of arrival pickup time will be used as the primary measure of the quality of service, because as students are waiting to be picked up, or as students need to get to school on time, they don't want those times to vary very much. And it'll be a hypothesis test with alphas equal to 0.01. So that will be your level of significance. Your alpha is 0.01, which means your confidence coefficient will be 0.9 or 90%. And to see if the variances are equal for the Millbank Company and Gulf Park. So our null hypothesis, again, equality goes in the null hypothesis, is that they're equal. And you could also say we're just going to start from the assumption that that's the status quo, the current state, that they provide equal service. And the alternative is that the variances are not equal. So here we have a sample of 26 for Millbank, 26 arrival times for Millbank with a sample variance of 48. And then we have 16 sample size from Gulf Park with a variance of 20. So when you put together this test statistic right here, and I'll just copy this and put it over here and add it like right over here, and maybe I'll just make it a little smaller. And there we go. As you do this test statistic right there, I'll put it here so it's a little bit bigger. As you do that test statistic here, you get to determine, you have to figure out, that's the way I want to say it, which goes in the numerator and which goes in the denominator. Numerator's in the top, denominator's in the bottom. And you want to put the larger one in the top so that you get a bigger number. So sample variance of 48 and sample variance of 20, we're going to put 48 in the numerator and 20 in the denominator. 48 in the numerator, 20 in the denominator gives us 2.4. All right, well with 2.4, we could start to put this together right here. And I'm just going to move this over. So I'm just going to grab this presentation. And I'm going to see how much I can move it over. And that's pretty good. And now we have to do this one here. So our degrees of freedom, right? We had in the numerator, we had 48, and that had 26 for the sample size. So in the numerator, we're going to have 25. So the way you do your degrees of freedom is 25 up here and then 15 down here. And that's just the way I think about it. It's actually 2 degrees of freedom. And you could just cancel out that. I'm actually going to do a little, I shouldn't have put that in there. I was just kind of doing it all at once. And it was a little bit late. And so I'm just going to do that like this and take this. And then I wonder if there's a way I could color match. So I'm going to go here and I'm going to grab this. I'm going to grab that color. And then I'm just going to get rid of the border. I'm going to say none. And that's great. That's how you do magic with digital stuff these days, right? So our degrees of freedom are going to be 25 in the numerator and 15 in the denominator. And so we need 25 in the numerator, which we've got right here, and we need 15 in the denominator. So here's denominator degrees of freedom. And we've got 15 right here, right? Because it's like 26 minus 1 and 16 minus 1. So we got 25 and 15. So here's 15, and we need that. We need that at alpha is 0.05 right here, okay? And so we go, because that's what the upper tail is, and so we'll just look at the upper tail first right here. And so we go 15 degrees of freedom in the denominator, and it's 0.05, and we bring that over here to 25. And 25 is this information right here, and there's 0.05 with 25 in degrees of freedom in the numerator. And so that gives us that value right there, which I just crossed out, and you can't see it's 2.25. And so we have 0.05 is our p-value, and we have, let me see here, did I get that right? No, sorry, it's 2.28. So that's the 25 right here, it's 2.28. And we have 2.28 as our F value or our critical value. And then when we calculate our statistics, we got 2.4. So we put 2.4 here as our F value. And that's more than 2.28. And if we look at where's 2.4 in this 0.05 area, 2.4 is right there, actually. It's going to be between, 25 here in the numerator and 15 there. 2.4 is going to be between these two values here, between 2.28 and 2.69. 2.4 will be between that. So that'll be between 0.05 and 0.025. And so it'll be less than 0.05 because it's between 0.05 and 0.025. And so that's how I write that. And you can see both of these, whether we use the p-value approach or the critical value approach, which is using the F value as your test statistic and your critical value, right? That's the critical value. This is your test statistic. Whether you use the critical value approach or the p-value approach, both of these fall into the reject area. So we reject our null hypothesis. And so we don't say that they're equal. We say that the variances in the two populations are not equal. And if we look at how they do this, right, here's using the p-value. And, they do it their own way, which I don't really like the way it doesn't really make sense to me. And the null hypothesis is rejected. So I'm just going to get this here and highlight this because I want that to be highlighted. And I'll do that and just make this a little bit bigger here. And then I'm going to get rid of the fill there. And I'm going to make this bright yellow. I'm going to make it 8, right? So the null hypothesis is rejected. And I'll copy that just in case I want to highlight the next one. And that's using the p-value approach and using the critical value approach. Again, they reject the null hypothesis. And this one, I could just put the border right on that image. And we'll make that 8 like that. So that's reject the null hypothesis. So here is just that same, what is this? The F table. And then here, the conclusion, the two buses differ in terms of pickup delivery time variances. So we reject the null hypothesis based upon both approaches. And so at this point, you could say, hey, the variances aren't equal, and you could start to look at the data and try to figure out, you could figure out which one offers the least variance. And but what you tested here is just that they aren't equal with 90% confidence, right? Confidence level. So 90% confidence level, 90% confidence coefficient. The variances of these two bus services are not equal. All right, so that's how you do hypothesis testing about the variances of two populations. And again, what you're learning here are just tools you could use in different situations. And you're starting to think about how you can use data and statistics to make better decisions, whether you're trying to determine which bus service to select, or whether you're trying to determine things like these situations right here, which we went over at the beginning of this video, right? Statistics can help you start to use data and statistics to make better decisions. And that's powerful. It's powerful. And, it could, change the way you do business and change how much money you make, which is amazing. All right. See you next time.